Recitation 8 will review Chapter 6, where we looked at the nature of light. We also talked about relating the frequency of light to the wavelength and energy of that light. Other main topics that were of interest for this were understanding the photoelectric effect and understanding the origin of atomic emission spectra, as well as finally introducing quantum mechanics and how we understand the shape of orbitals today and where electrons reside today and how we think about that today. So I'm going to try something a little bit different with this recitation. I already have the answer key typed out, so I'm just going to work through the answer key that's typed out as opposed to writing out every problem step by step. So the two main equations that we covered this week were the speed of light equals frequency times wavelength, and energy equals Planck's constant times my frequency. And the main takeaway that we should remember from these two equations is the inverse relationship between wavelength and frequency, because the speed of light's a constant, so if I increase the wavelength, I need to decrease the frequency of that light. And the other relationship that we should remember is the relationship between frequency and energy. Here, I have a direct relationship between frequency and energy. As frequency increases, H is Planck's constant, that stays constant, so as my frequency increases, my energy will increase. And we can rearrange this equation to solve for frequency, and then I can plug in frequency into energy equals Planck's constant times frequency. I can just put this right in place of frequency to get an equation now that allows me to relate my wavelength to the energy directly without having to go through frequency. Another important aspect is kind of figuring out how this fits into the electromagnetic spectrum and what that means for different regions of the electromagnetic spectrum. And so below we have the visible region of that electromagnetic spectrum. Important thing to know, in the red region versus the blue region, right? So red region versus the blue region. Blue is about 400 nanometers. So 400 nanometers is a shorter wavelength. Because it's a shorter wavelength, because I have a shorter wavelength, I have a higher frequency. And because I have a higher frequency, right? Higher frequency, higher energy when compared to red light, right? Red light over here, energy equals my speed of light equals the frequency times my wavelength. Energy equals Planck's constant times my frequency. So red light has a longer wavelength. Longer wavelength means a lower frequency. Lower frequency, lower energy. So we should be comfortable with that region and comparing different regions of the electromagnetic spectrum relative to their wavelength, frequency, and energy. Just thinking about basic relationships like that. And we related our observed emission spectra, right? We now know that we can relate the energy of light to the frequency of light, and we now know that that energy means something for the atom. And we can relate that to the emission spectra that we see. And so here's the emission spectra for hydrogen, where I get 4 distinct wavelengths of light. That represents 4 distinct transitions within the element for an electron within that hydrogen atom. And how that works is if I have an electron at a higher energy level, so n equals 2 or n equals 3 or n equals 4, anything above n equals 1. N equals 1 is our ground state, our lowest energy state. So any place above that is a higher energy. And when that electron relaxes down to a lower energy state, it's going to give off energy, and it's going to give off energy that's proportional to Planck's constant times the frequency. For some reason in this diagram they put frequency as an F when we really know frequency as nu. So now we know that in the emission spectra for hydrogen, these distinct colors that are given off, they represent distinct, specific, quantized transitions within the hydrogen atom. And we can calculate the change in energy required for each of those transitions. All right, so here's my first question for you. Sodium streetlights produce a yellow light with a wavelength of 589 nanometers. What is the frequency of this light, given that the speed of light equals frequency times my wavelength? And I know the speed of light equals 3 e to the 8 meters per second. So to answer this question, we're given our wavelength in 589 nanometers, but my speed of light is in meters per second. So the step number one should be to convert nanometers into meters. So I know within 1 meter I have 1 billion nanometers. So I'm going to divide by 1 billion nanometers, 1 e to the 9th nanometers, to get 5.89 e to the negative 7 meters. Now, the next step, all I did was rearrange that equation, right? The equation was speed of light equals frequency times my wavelength. We want to find the frequency, so I divided both sides by wavelength. Wavelength cancels out, so I'm left with frequency equals the speed of light over wavelength. So that's all I did down here, was take frequency equals the speed of light, 3 e to the 8th meters per second, divided by the wavelength in meters. Taking a look at the units, right, my meters cancel out, which is good because I'm looking for a frequency, which should be inverse seconds. 3 significant figures, 589 here, 3 significant figures in my final answer, 5.09 e to the 14th inverse seconds. Another question based on that sodium streetlight, right? That sodium streetlight that gives off that yellow light with a wavelength of 589 nanometers. What is the energy of 1 photon of this light? Given that energy equals Planck's constant times frequency, and Planck's constant is 6.626 e to the negative 34 joules times seconds. Well, this is a pretty straightforward calculation. Right, I've got energy, I've got Planck's constant, and I've got my frequency. So that's my equation, and I know 2 of those. Planck's constant, it's a constant, and I just found my frequency in the previous calculation. So energy equals Planck's constant times my frequency. Multiply those 2 together, keeping track of my units, and I'll see that joules are the only unit that remains. Seconds cancels out. And that's good because I'm looking for energy. Energy should have a units of joules. Again, I would go to 3 significant figures because our original calculation, 589, was based on the number 589 nanometers with 3 significant figures. So I should have 3 significant figures in this final answer. So the energy of 1 photon of light, of this yellow light at 589 nanometers, is 3.37 e to the 19 joules. Here's another question on relating frequency to wavelength to energy. Current cell phones are based on 4G technology, and so 4G, depending on your phone, 4G technology works at around 880 megahertz of a frequency. Many networks are currently moving to a 5G technology that operates on a higher frequency. And again, there's different ranges to the 5G range. So one of them right now that's in use is 25 gigahertz as the frequency of this 5G technology. What are the wavelengths of each signal in centimeters? So what's the wavelength of 880 megahertz in centimeters, and what's the wavelength of 25 gigahertz in centimeters? Again, given that the speed of light is equal to frequency times my wavelength, and speed of light is 3 e to the 8th meters per second. Well, this calculation is a little bit more involved because I've got megahertz for both of those. So I first have to go and do my calculation for 4G, and then I'll do the same series of steps for 5G. So 4G megahertz. In 1 megahertz, there are 1,000,000 hertz, so 1e6 hertz. So I have a frequency of 8.8 e to the 8th hertz. Hertz and inverse seconds are interchangeable, right? So my frequency is also 8.8 e to the 8th inverse seconds. I want to find the wavelength of that. So again, I just rearrange that equation. Wavelength equals frequency. Speed of light equals frequency times wavelength. I want to find wavelength, so I'll divide both sides by my frequency. Frequency cancels out, and I get wavelength equals the speed of light divided by my frequency. That's the calculation that we did here. So wavelength equals the speed of light divided by my frequency. And that gives me my wavelength. My wavelength happens to be about 0.34 meters. And I asked for that in centimeters. Well, I know in 1 meter I have 100 centimeters. So I multiply 0.34 by 100 to see that the wavelength is actually 34 centimeters. Two significant figures because I only have two significant figures here, right? 880 as written is two significant figures. Do the same series of steps with the 25 gigahertz, except for 1 gigahertz is 1 billion hertz. So I multiply by 1 e to the 9 hertz to get rid of the gigahertz. After that step, I've got 2.5 e to the 10 hertz, and again, that's interchangeable with inverse seconds, so 2.5 e to the 10 inverse seconds. Use my rearrange equation to find my wavelength, speed of light divided by my frequency, and I get a wavelength of 0.012 meters, which when converted into centimeters, gives me a wavelength of about 1.2 centimeters. So something a little bit more narrow than your thumb, right? The width of your thumb is pretty close to 2 centimeters. So this is a little bit less than that. So 1.2 centimeters would be the wavelength of 25 gigahertz. For this unit, you should be comfortable converting hertz to megahertz, gigahertz to hertz, as well as nanometers and meters, maybe even micrometers or picometers. But there are probably 4 or 5 metric conversions that you should be very comfortable with. Joules to kilojoules as well, but hopefully we're all comfortable with going from kilo to the base unit. So it'd be the same as kilogram to gram or kilometer to meter when we go from kilojoules to joules. All right, let's now compare the energy of those two networks. Let's compare the energy of 880 megahertz frequency versus the 25 gigahertz frequency. Compare the energy of 1 mole of photons from each signal. Given that energy equals Planck's constant times my frequency, and Planck's constant is 6.626 e to the negative 34 joules times seconds. The main reason for going from 4G to 5G is it allows for faster download speeds, it allows for faster upload speeds, and so it improves your ability to access technology on your mobile device, basically. It allows for more capability on that bandwidth, on the 5G bandwidth versus the 4G. So here's that calculation, right? For the 4G, here's my Planck's constant times my frequency that I found from the previous page, the previous problem. So that energy ends up being about 5.8 e to the negative 25 joules. The key, though, for the next step is that is that many joules for 1 photon. So to figure out how many joules I have for a mole of photons, right? A mole of anything is 6.02 e to the 23 photons. A mole of carbon atoms, a mole of electrons, a mole of photons, a mole of quarters would all contain 6.02 e to the 23 of that item. So I want to multiply by Avogadro's number. Photon cancels out, and I'm left with the energy in joules per mole. So about 0.35 joules per mole is the energy of the 4G frequency. Do the same steps for 5G, multiply by Planck's constant times the frequency that I found in the previous question. I get about 1.7 e to the 23 joules per photon. Again, when I do that calculation, right, bring in Avogadro's number, photons cancel out, and now I have joules per mole. And I get an energy of approximately 10 joules per mole That's the energy associated with a 5G signal of about 25 gigahertz. Should be pretty comfortable with these steps, especially the last step. So we've covered moles and what that means, and so how to relate that energy in terms of joule per mole, because that's more often what we see the energy as, especially thinking about something like a chemical bond, for example. So my next question for you is to compare the energy of 1 mole of photons from 4G versus 1 mole of photons at 5G. Right? Many people right now are fighting the switch to 5G technology over the concern of the energy and saying it's going to cause some detrimental damage to their health, this 5G technology. So what would you say about this argument, right, given the energy of 4G is approximately 0.35 joules per mole, and 5G is approximately 10 joules per mole. So what would you say about that argument, or what would you say about the concern of this energy level? Right, so for example, one thing we are familiar with is the energy in a chemical bond. So the average energy in a chemical bond is 374 kilojoules per mole, right? Much greater than the energy of 4G or 5G networks. So yes, 5G is a greater energy. That being said, it's still quite a ways away from the energy required to break a chemical bond. And if you think about it, right, this is the energy that's being put off by your cell phone while you're using your cell phone. So if you are worried about this energy, right, maybe you shouldn't use a cell phone, or maybe you shouldn't have a cell phone, because you're being exposed to that energy anytime you're using the device. Next question for you. Calculate the energy and wavelength in nanometers of a photon of light emitted from a hydrogen atom when an electron falls from n equals 5 to n equals 2. Given that Planck's constant times the speed of light times Rydberg's constant is 2.18, 10 to the negative 18 joules. Well, for this calculation, the important thing to take note of is that we fall, the electron's falling from n equals 5 to n equals 2. So my initial quantum level is n equals 5, my final quantum level is n equals 2. So for the calculation, right, final minus initial, so final is 2, the 2 would go down here, the initial is 5, that would go down here. Then I plug in Planck's constant times the speed of light times Rydberg's constant out here, the negative stays. So I get 1 over 2 squared minus 1 over 5 squared. So I square that, I get 1 over 4 minus 1 over 25. Subtract, and then multiply to get an energy. And the key here is that this energy is the energy of the electron. So the electron, when it transitions from n equals 5, which is a higher energy level, to n equals 2, which is a lower energy level, I'm going to lose 4.58 e to the negative 19 joules. And how I'm going to lose that energy is by releasing a photon of light, and that photon of light will have an energy, right, of 4.58 e to the 19 joules. Now that I have energy, now I can use my second calculation, my second equation, which is energy equals Planck's constant times the speed of light divided by my wavelength, right? I rearrange that to solve for wavelength. So rearranging that, I get wavelength equals Planck's constant times the speed of light divided by my energy that I just found. So my wavelength equals Planck's constant times the speed of light divided by the energy. Taking a look at the units, right? For the units, energy cancels, seconds cancel, and that's good because I'm looking for a wavelength. Wavelength should be measured in meters. I get a wavelength of 4.34 e to the negative 7 meters. I asked for the wavelength in nanometers, so we're not done there. One more step, one more calculation. We have to convert meters to nanometers. So to do that, right, I know in 1 meter I have 1 billion nanometers, so I multiply by 1 e to the 9 to get my wavelength of approximately 434 nanometers, which happens to be in the blue region. Again, should be a very straightforward calculation as long as you remember N initial, N final, and how to convert nanometers to meters, meters to nanometers, and realize that the energy that we're calculating at first is the energy of the electron. We're looking for the energy of the photon. So it has the opposite sign of that because the electron releases that energy, the electron loses that energy in the form of a photon of light. All right, last calculation for you. What is the wavelength in nanometers associated with a neutron that is moving at 2.3 e to the 2 meters per second and has a mass of 1.675 e to the negative 27 kilograms? Given that the Planck's constant here is 6.626 e to the negative 34 kilograms times meters squared divided by seconds. So this is de Broglie wavelength. De Broglie looked at Einstein's work and Planck's work, and he said that because Einstein applied properties of matter to light, why couldn't de Broglie apply properties of light to matter? Why couldn't matter also have a wavelength? And the key to this calculation is it only works for things with incredibly small masses, right? Because this I have mass and I have my velocity. So things that are incredibly small, things on the atomic and subatomic scale, have a measurable wavelength, whereas things on our scale that are incredibly large in comparison do not have a measurable or noticeable wavelength. So for this calculation, I've got my wavelength equals Planck's constant. I need to have the different units of Planck's constant where I've changed joules. I've changed the energy of joules, and I've converted the units of joules into kilograms times meters squared because I need to have a mass in kilograms in de Broglie's calculation. I need to have kilograms cancel out. So certainly that helps me allow kilograms to cancel out. Seconds also cancel out, and then the meters cancel out, canceling out one of those meters, and that's good because, again, I'm looking for the wavelength. Wavelength should be measured in meters. It's a distance. And I find a wavelength of approximately 1.7 e to the negative 9 meters. Two significant figures because the speed of the electron is moving. There's two significant figures. So 2.3 e to the 2 meters per second. Two significant figures there, two significant figures in this answer. And that's meters. I want to convert that to nanometers. So again, the same conversion. For every 1 meter, I have 1 billion nanometers. So multiply by 1 e to the 9th to get a wavelength of approximately 1.7 nanometers. Right, again, so this is a scale that you can measure and detect because that applies to things that have incredibly small mass, right? 1.675 e to the negative 27 kilograms is incredibly tiny compared to the scale that we are on. So de Broglie's wavelength, if you're given a velocity, if you're given a mass in kilograms, you should think, I have to calculate de Broglie's wavelength. That's the only time you'd calculate de Broglie's wavelength. You'd have to be given velocity and mass in kilograms. So the important things from today, right? Nanometers to meters, know those conversions, or meters to nanometers. Megahertz to hertz, gigahertz to hertz, right? Joules to kilojoules. All of those conversions, I will guarantee you right now today, will show up on the next exam. And the other thing to remember is that hertz, right, we can go directly from hertz, right? 1 hertz is equal to 1 inverse second. So again, also those units are interchangeable.